In the previous tutorial, we discussed about the nodes level of abstraction. Here, we move to the next level of abstraction, which is agents level. Agents allow you to create graphs of modules from the previous level of abstraction. Essentially, agents support multitasking, meaning that each agent comes with several tasks, and each task will get its own designated graph of nodes from the previous level of abstraction. We allow sharing the nodes between the tasks of a given agent. This will lead to enhancing the functionalities of the agents as well as saving resources. In this tutorial and the next two tutorials, we cover the basic things that you need to know in order to build agents. In particular, we show you how to build an image classifier agent. This agent uses its internal data source in order to train its internal deep learning classifier model. In addition to the train task that is used by the agent to train its internal deep learning model, this agent comes with two other tasks, the visualization task and the evaluation task. In this tutorial, we show you how to build the basic structure of the train task of the agent. The train task of the agent consists of the dataset node, the model itself, and also the evaluation node and the logger node. In the next tutorial, we show you how to add the loss node to the train task and an optimizer node in order to actually train the model. Finally, in the last tutorial, we show you how to rely on multitasking aspect of the agents in order to add other tasks to the agent. Okay, let's start. In order to create customized agents, we rely on agent construct. This is an agent construct. First, we save our image classifier agent as MNIST. Next, we try to switch to the graph interface in order to inspect the graph underlying of the agent, but we get an error message from the system. This error message is saying that we need to set the tasks parameter of the agent construct, and we haven't done it yet. Agents support multitasking, and that is why the tasks parameter is actually a list of tasks. We add the first task and we name it train. This time that we click on graph button, the system doesn't give us error anymore, and instead it asks us for which task we want to see its graph. Here we have a single option because our agent has a single task named train. At the beginning, the train task doesn't have any nodes. MNIST CLS node is the first node that we add to our graph from our personal library. This node is an image classifier network that we created in our MetaGraphs tutorial part 1. Next, we add a dataset node to our graph. We name it MNIST train. The dataset node allows you to bring different data sources into your graph. Here, our goal is to use this dataset node in order to connect to MNIST dataset. That is why we set the built-in dataset to MNIST. Next, we set the batch size to 32. By default, the output of this dataset node will be a list with two entries, where the first entry is the image and the second entry is the label. However, we prefer the output of this dataset node to be a dictionary with two keys, image and label, where the image key refers to the image tensor and the label key refers to the label tensor. Adding image and label to the keys parameter exactly does that. Here we have an issue because the output of the dataset node, as we just explained, is a dictionary, and on the other hand, the MNIST node expects its input to be an image tensor. Therefore, we need an adapter node between the dataset node and the MNIST node. This adapter node takes the dictionary generated by the dataset node and allows us to pick the image tensor from it and pass it to the MNIST node. The adapter node is the inputs mapping node. We name it pick image. Index 0 specifies from which incoming edge of inputs mapping we want to pick the target. Given that this inputs mapping node will have only one incoming edge from the dataset node, then index 0 should be 0. What's being delivered on each incoming edge is a list of lists of objects in this level of abstraction. So they are double nested lists. The index 1 parameter refers to the index for the outer list, and the index 2 parameter refers to the index for the inner list. Here we set both index 1 and index 2 parameters to 0 because the dictionary generated by the dataset node will be wrapped inside two lists where both lists have a single entry. Okay, index 0, index 1, and index 2 allow us to pick the dictionary object from the output of the dataset node. However, we are not really interested in the dictionary object. We wanted to pick the tensor image from it. That is why we set the input type to mapping. That refers to the fact that the picked object from the output of the dataset node will be a dictionary. Also, we set the output type to be tensor because we want this adapter node to output the tensor image. The last parameter that we need to set for this inputs mapping node is the keys parameter, and we need it to set to image because that's the key for the image tensor. Okay, so far we have added the essential nodes to our graph, which are the dataset node, the adapter node, and the deep learning node. But before running any serious training job, I just want to make sure that this graph actually works. And in order to do so, I want to use the logger node. The logger node allows you to capture and inspect the outputs generated by different nodes. I name my logger node test logger. In the beginning, I just want to capture the output of the MNIST node. That's why I connect the MNIST node to the logger node. Now I need to configure the logger node how to interpret and store the outputs coming from the MNIST node. The db fields parameter of the logger node is the list of db fields, where each db fields in that list is corresponding to an incoming edge. For example, if the logger node has two incoming edges, then this db fields parameter needs to have two db fields configs. In this case, since the logger node has a single incoming edge, the db fields parameter needs to have a single db fields config. Okay, now we are adding configs for this specific incoming edge. Here I have the option to add several logs corresponding to this incoming edge. That is why that db fields parameter here is a list of db field configs. In the beginning, I just want to add a single log corresponding to this incoming edge. This single log will be the softmax distribution generated by the MNIST node, and also please note that the type of this log will be a number because the softmax distribution will be a vector of floating numbers. We choose ypred as the name of this log entry, and that's how it will appear in our logs. The output of the MNIST SNet node, similar to any other nodes in the agent graphs, will be a list of lists of objects. In particular, the softmax tensor will be inside two lists where each list has a single entry. Here, the outer index parameter refers to the index for the outer list, and the inner index parameter refers to the index for the inner list. Therefore, we set both of them to 0. We do not need to set the index and key parameters because the object that will be picked by the outer index and inner index will be the softmax tensor directly, and it is not going to be a dictionary or a list, so we don't need to set index and key parameters. Okay, now we want to see if the graph that we just defined as the train task of this agent actually works. In order to do so, I need to add this agent to a system, which is the next level of abstraction, and then execute that system using jobs. Okay, I switch to the next level of abstraction, which is the system level of abstraction, and I create a new system called MNIST system. Systems are similar to the agents in the sense that they also support multitasking. When you define the tasks for the agents, essentially they are graph of metagraph nodes. However, when you define tasks for the systems, they are graphs of agents. Here my goal is just to add a single task for this system and then make that task to have a single agent node that we just created. When I click on the graph button, the system is telling me that something is wrong and I haven't added any task to my system config. We add a new task and we call it MNIST. Next, we go to the graph interface and we add the MNIST agent that we just created, and it is part of our personal library, to this system task. Now that we have the system, let's use the jobs in order to execute it. Switching to jobs, we create a brand new job called MNIST job. Each job has two main parameters, system and sessions. System parameter specifies which system to execute, and sessions parameter specify how to execute that system. We choose MNIST system as the system that we want to execute. The next step is to specify the sessions parameter. Please note that the sessions is actually a list of sessions. What it means is that a job is defined actually as a sequence of sessions, and execution of a job is equivalent to execution of those sessions one by one. For our first job, we just wanted to have a single session. That's why we just add a single session object to it. Two parameters of sessions are system tasks and agent tasks, and they are there because we allow systems and agents to perform multitasking. System tasks specify which specific task of the system we want to execute, and agent tasks specify which specific tasks of the agents as part of that system task we want to execute. We choose train as the name of this session. The next thing to specify is the system task. And as you remember, for the MNIST system, we just define one single task. But unfortunately, I don't remember the name that I chose for that system. In order to find out the name of the task that I defined for the system, I go back to the system level of abstraction. Here I see that the name of the task is MNIST. Good. Also, as part of the session config, I will need the name of the agent and also the task name of the agent. Therefore, we go to the agent's level of abstraction and figure out those names as well. The agent name is MNIST and the name of the task of the agent is train. Now we have all the names that we need in order to specify the session config of the job. The system task is MNIST. As part of agent tasks parameter, I need to specify the tasks for all the agents that are part of this specific system task. The MNIST system task has a single agent node, which is MNIST agent node. And for that agent, we want to execute its train task. Essentially, agent tasks parameter is a dictionary mapping the agent name key to the task of those agents that you want to execute. That is why here we add MNIST as the name of the agent to be the key and train as the task of that agent to be the value. Perfect. We just added all the details that we need to execute our job. We click on Run button. The system is telling us that the job is being successfully submitted and the run ID corresponding to this job is 428. We have access to the finished and active runs via Runs tab. Clicking on Runs tab, we go all the way down to find a run with ID 428. We click on the run in order to see its status and its logs. What we see is the bad news. The job actually failed. When we hover our mouse over the failed status, we see the message corresponding to the failure. Here, the system is telling us that a convolutional filter was expecting that its input feature map to have 3 channels, but it received an input feature map with just 1 channel. It goes back to our classifier network. In fact, the first convolutional filter of the feature extractor of the classifier network has input channel size of 3, whereas the MNIST dataset images are grayscales and therefore have the channel size of 1. Okay, let's fix this issue. In order to resolve this issue, we need to go to our agents and make the classifier node of that agent to accept images with the input size of 1 instead of 3. The classifier node is MNIST CLS net node. This metagraph node has essentially 2 nodes, the classification head node, which is called MNIST CLS head, and the feature extract node, which is called the ResNet 34 smaller. We need to modify res34 smaller. Res34 smaller has 3 internal stage nodes and 1 input stage node. We are interested in the input stage node because this is the node that first processes the input images. And this is where that we have the issue. Okay, let's see what is happening inside this stage node. Essentially, the internal block of this stage node has three layers. And the first layer is the cause of the issue. Oh, we got it. We just need to change the input channel size of this convolutional filter from 3 to 1. We save our correction into the agent. Now that we have corrected our agent, we need to make the MNIST system to use this new version of the agent. In other words, the MNIST system will not use this new version of the agent unless if we force it. What it means is that the MNIST system is using the snapshot of the agent at the time that we added that agent to the system. Therefore, the system doesn't use this new snapshot of the agent that we just created by saving our correction to the agent. Please note that this behavior is not specific to systems and agents. It's actually a common pattern across all the abstractions level in our platform. Every time that you use modules from previous level of abstraction in higher level of abstraction in order to create new modules, you get the snapshots of the modules from the previous level of abstraction at that time. And the changes that you make in the modules from the previous level of abstraction do not automatically reflect in the modules from the higher level of abstraction that use those modules from the previous level of abstraction. Okay, what we need to do now is to remove the MNIST agent from the MNIST system and then add it again from our personal library. Doing so, we will get the new snapshot of this agent with the correction. We need to do the same thing for the system parameter as part of the job config. In other words, the MNIST job has access to the previous version of the MNIST system, not the new version. Therefore, we first remove the MNIST system and then add it again. Let's run our job again. Hopefully this time we don't get any error. Good. The run status is finished and not failed anymore. Now that the job finished successfully, we want to inspect the logs stored by the logger node. In order to do so, we click on Logs button. In the Logs window, from the drop-down Log Source menu, you could choose the logger node that you want to see its stored logs. Test logger is our only logger node. Here, batch index refers to the execution index. For example, if you have a training job with 10 example batches, then the batch index could be any number from 0 to 9. In the next section of the logs window, you have access to the different fields that you have added as part of the configs for the logger node. For example, in this case, we added YPRED as a numbers field. Perfect. We are able to see the softmax distribution generated by the deep learning model as part of the MNIST agent. Okay, this shows that our graph actually works. So far, the logger node as part of the agent only captures the softmax distribution generated by the classifier node. What I want to do next is to make this logger node to also capture the input image as well as the ground truth label corresponding to that input image. So I start changing the MNIST agent. The first step is to add an edge from the dataset node to the logger node. Next, we need to add the DB fields corresponding to this new incoming edge. As part of these new DB fields, I want to add two new DB fields, one for image and the other one for the label. The field type for the image should be image. The outer index and inner index parameters are set to 0 because the dictionary generated by the dataset node is wrapped inside two nested lists where each list has a single entry. The picked up object by the outer index and inner index parameters is a dictionary, therefore we need to set the key parameter. We set the key to image, which is the key corresponding to the image tensor in generated dictionary by the dataset node. Next, we add the label DB field corresponding to the ground truth labels from the dataset node. First, we make the MNIST system to use this new version of the MNIST agent. We make MNIST job to use the new version of MNIST system. We run this new version of MNIST job. As you can see, different from before that we had only ypred as logs, now we have also ytrue and image logs. Each row here corresponds to a single example, which consists of its input image, its predicted softmax distribution, and its ground truth label. As of now, the predicted softmax distributions are just random numbers. It is because we did not train the model as part of this agent. Before training the model, I want to measure the performance of this randomly initialized model. In order to do so, I need to change my agent and add an evaluation node to its graph. We drag and drop the eval node on canvas. We name it train eval. Now the system is telling us that we need to set the eval parameter of the train eval node. We set the eval parameter of the eval node. Now the system is telling us that we need to set the in node's parameter of the eval parameter of the eval node. The inNode parameter specifies the incoming edges for this eval node. Essentially, it is a list and its length should be equal to the number of the incoming edges for this eval node. We want this eval node to have two incoming edges, one being connected to the dataset node getting the ground truth label, and the other one being connected to the MNIST net node getting the predicted softmax distribution. First, we add the inNode parameter corresponding to the incoming edge from the dataset node, and we name it yTrue. Next, we will add inNode parameter corresponding to the predicted softmax distribution coming from the MNIST net node. Please note that when we want to set an inNode parameter, we are given two options. The first option is graph-based config, and the second option is a string. For this example, and for both the incoming edge from the dataset node and the incoming edge from the MNIST net node, we go with the string option. This is the default option, and you should also choose it for the majority of the eval nodes that you will be developing. You should only use graph-based config if the predictions or the ground truth labels need pre-processing before being used in order to compute the evaluation metrics. Now the system is telling us that we need to either set evals or nodes parameter of the eval parameter of the eval node. For the majority of the evaluation nodes that you will be developing, you only need to set the evals parameter, not the nodes parameter. You only need to set the nodes parameter if the evaluation metric that you are trying to compute is not being captured by the default evaluations option provided by us. Please note that the evals parameter is a list of eval configs. What it means is that a single evaluation node could compute several evaluation metrics. Here our goal is to add a single evaluation config to compute the accuracy of the classifier network. The first parameter that we set here is ypred inNode, which is essentially the inNode name that we chose for the incoming edge corresponding to the predicted softmax distribution. The ypred outer index and ypred inner index parameters are set to 0 because the predicted softmax distribution by the MNIST node is being wrapped inside two nested lists where each list has only a single entry. The object being picked up by the ypred outer index and ypred inner index will be the actual softmax tensor, therefore we set the ypred type to tensor. Next, we need to set these parameters for the incoming edge from the dataset node, bringing the ground truth label. In the case of the ground truth labels, the object being picked up by the yTrue outer index and yTrue inner index parameters will be a dictionary because of how we set up our dataset node. That is why we need to set the yTrue type parameter to mapping. After setting the yTrue type parameter to mapping, next we need to set the yTrue key parameter, which refers to the key of the ground truth labels in the dictionary. Finally, we are ready to set the actual evaluation metric. We choose the evaluation metric to be accuracy. The system doesn't complain anymore about the eval node. We attach the dataset node and the MNIST net node to the eval node. Clicking on the connection button, we see that the first incoming edge for the eval node, which being referred as input 0, is set to MNIST train, which is the dataset node, and the second incoming edge for this node, which is referred to as inputs 1, being set to MNIST node. Next, we check to see if this order of the incoming edges for the eval node matches the innode's parameter of the eval parameter. The first in node is set to y true, which is correct, given that the input 0 being set to MNIST train, which is the dataset node. The second in node is set to y pred, which matches inputs 1 being set to MNIST net node. We update the MNIST agent of the MNIST system to capture this new version of the MNIST agent. We update the MNIST job with the new MNIST system. Let's run the job. Now, the log source dropdown gives us two options. The test logger, which is corresponding to the logger node that we have in our graph, and the second option is the train eval logger, which is corresponding to the internal logger of the train eval node. Choosing the train eval logger, we see the accuracy computed by this evaluation node. We still have access to the logs captured by the test logger node. The computed accuracy by the evaluation node is corresponding to a single batch of 32 examples. What I want to do next is to compute the accuracy over all the examples in the MNIST training dataset. Given that the MNIST training dataset has 60,000 examples, I will increase the batch size of my dataset node from 32 to 1000 and the number of the steps of the agent from 1 to 60 in order to go over all the examples in this dataset. First, we change the batch size from 32 to 1000. Next, I remove the logger node since otherwise all the images in the dataset will be stored as logs. We change the number of the steps of the agent from 1 to 60 in order to cover all the examples in the training dataset. We update our system with this new version of the agent. We update our job with the new version of the system. We run the job. Computing the accuracy over all the examples of the training dataset, this job takes longer compared to the previous job. This is the accuracy for the whole dataset.